This video is basically a continuation of my previous video on Coulomb's law of electrostatics. In my previous video, we have seen that the electrostatic force between two point charges is given by Coulomb's inverse square law as F is equal to k q1 q2 by r square, where q1 and q2 represents magnitudes of the 2 point charges, r is the distance between them, and k is the constant of proportionality, which is also known as Coulomb's constant or electrostatic force constant. And we have also seen that this value of k varies from medium to medium, and so does the electrostatic force between two charged objects. And we have also seen that in case of vacuum or air, the value of k is approximately 9 into 10 to the power of 9 Newton meter square per Coulomb square. Whereas in case of medium, k varies from one medium to another medium and is overall less than that in vacuum. We can also write this constant k in terms of another constant called epsilon. Therefore, the force equation becomes 1 by 4 pi epsilon q1 q2 by r square. The reason for representing k in terms of another constant is mainly due to historical reasons, where the area of the sphere, that is 4 pi r square, is incorporated in the denominator. Here the epsilon gives us the permittivity of the medium in which the charges are placed. But what is permittivity? Permittivity can be considered as a measure of resistance offered by the medium to the electric force. So greater the permittivity of the medium, greater is the resistance offered by the medium to the electrical forces between two charged objects. So in case of vacuum, epsilon becomes epsilon naught, whose value is approximately 8.85 into 10 to the power of minus 12. Whereas in case of medium, the epsilon m of a medium can be represented as a product epsilon naught into epsilon r. Epsilon r is the relative permittivity of the medium with respect to that of vacuum. That means if the charges are brought from vacuum and placed in a medium as shown in the figure, the force between the 2 point charges or charged objects drops by a factor of epsilon r. So if you have two charged objects q1 and q2 initially placed in vacuum, let the force between them be Fv, given by 1 by 4 pi epsilon naught q1 q2 by r square. Now these two same charges are now brought and placed in a medium having a relative permittivity of epsilon r. The force between them drops by epsilon r. That means Fv becomes Fv by epsilon r in case of medium. We have also seen that Coulomb's law is an inverse square law. That means the electrostatic force between 2 point charges is inversely proportional to the square of distance between them. That is, F is proportional to 1 by r square. So if the distance between the charges double, the force drops by 4 times, and if it's tripled, it drops by 9 times. So inverse square law states that if the distance between the point charges increases, force drops at a rate of 1 by r square. Now let's pause for a moment and ask ourselves an interesting question. What is a point charge? Well, there is no such thing as point charge, as every object occupies certain volume. So in reality, whenever we say that two charges are point charges, it means that the separation distance between them is far greater compared to their individual sizes. So you can see that two charged objects the size of our sun are separated by a very large distance compared to their individual sizes. So these two charged objects, despite their large individual size, they behave as point charges because of large separation compared to their individual sizes. Now let us explore some of the limitations of Coulomb's inverse square law. The first limitation is that Coulomb's law works only for spherically symmetric charged objects due to the inverse square nature of the electric field. That means it works for a point charge. It also works for a charged metallic sphere having a uniform charge distribution on its surface. But originally we defined Coulomb's law as that which works for point charges, but now we are saying that it applies to all spherically symmetric charged objects. So what is correct? We can say that a point charge is in fact a spherically symmetric charged object having near zero radius. Hence, Coulomb's law was safely defined using point charges because point charge itself is a spherically symmetric charge having zero radius. Whereas in case of non-point charges or extended charges, inverse square law may or may not work. It cannot be guaranteed because the electrical field can be spherically asymmetric. If the electrical field around a charged object is spherically asymmetric, then Coulomb's law is not valid. So Coulomb's law primarily works for spherically symmetric charged objects. The second limitation of Coulomb's law is that it works only when the charges are at rest with respect to each other. So I repeat, the Coulomb's law works only when charges are at rest with respect to each other. Suppose if there are two charges having same velocity v with respect to a static reference frame, then these objects are still at rest with respect to each other. Therefore, Coulomb's law is valid. So in the figure you can see that there are two charged objects having equal velocities v. That means they are at rest with respect to each other. So Coulomb's law is valid. But if the two charged objects have different velocities, then the Coulomb's law fails to work. This is because relativistic effects come into the picture, distorting the original Coulomb's force between them. This additional force called the magnetic force develops between them in addition to the electrostatic Coulombic force. The third limitation of Coulomb's law is that the point charges must be distinct and should not overlap. In the first case you see here, the point charges are overlapping. So Coulomb's law doesn't work. Whereas in the second case, the charges are distinct. So Coulomb's law works for them. Now let us see some of the applications of Coulomb's law or Coulomb's forces. Firstly, as we all know, Coulomb's law helps us calculate forces between different charged objects. Although we have defined Coulomb's law for point charges using various techniques such as integration, summation, we can find Coulomb's forces between two charged objects. Second is that Coulomb's forces or Coulomb's law lays the foundation of theory of electromagnetism. Imagine we did not study Coulomb's forces. It becomes difficult for us to understand electricity and magnetism because Coulomb's law lays the foundation of both electricity as well as magnetism. Thirdly, Coulomb's law helps us explore the microscopic and atomic dimensions because the atomic worlds are full of charged particles. So to calculate forces between them, we need to learn Coulomb's law. And lastly, Coulomb's law helps us to design several engineering devices, such as simple ones such as capacitors, diodes, transistors, to complex ones such as Xerox machine, photocopier technology, powder coating technology, etc. So several devices functioning is based on simple Coulomb's law or electrostatic law. Here are some of the additional properties of Coulomb's law. The first is that electrostatic force between two charges always form an action-reaction pair. So if charge Q1 exerts a force on charge Q2, say Fe, Q2 reacts with the same force Fe on charge Q1, which is equal and opposite. That means the electrostatic force between two charged objects always form an action-reaction pair. That is, they obey Newton's third law. Secondly, the electrostatic force between two charged objects always acts along the line joining the centers of the two charged objects. Thirdly, the electrostatic force is a conservative force, which means that work done by an electric force on a charge is path independent. We shall learn more about this conservative nature of electrostatic force in the next topic of potential energy. The fourth important point is, in the absence of external force, the momentum of a system of charged objects is always conserved. So you can solve problems using net momentum is constant in the absence of external forces. Now comes the main question: how do you experimentally verify the Coulomb's law? Well, we can do that using any force measuring device such as a torsion balance or a spring system. The discoverer of Coulomb's law, that is Charles Auguste de Coulomb, used a torsion balance system as shown in the figure to verify his Coulomb's law. I shall teach you about the detailed working of this torsion balance in another video. As of now, let us try to understand the underlying logic behind its working. So the process is simple. We have two spherical charged balls, initially uncharged. We want to prove the Coulomb's law using them. These spherical balls are usually metallic so that we can charge these spherical balls to desired value. One ball is attached to one end of a horizontal bar suspended from a torsion wire, whereas the other ball is free to move using our hands and is brought close to the first ball. So first we charge the ball which we have in our hand to some value, then transfer a portion of this charge to the ball on the bar. Usually both the balls get identical charges if they have the same radius. Now let's say both the balls have equal positive charge, so obviously they should repel each other. This repulsion causes the torsion bar to deflect horizontally through an angle, say theta. This theta is obviously directly proportional to the deflecting torque acting on the bar. That means theta is proportional to Td, that is the torque acting on the bar, which means it is proportional to the electrostatic repulsion between the two charged balls, that is theta is proportional to Fe. So in one case, let's keep the distance between the two charged balls constant and vary the charge. For each charge you find that theta varies such that theta is proportional to the product of the charge magnitudes. Theta is proportional to Q1 into Q2. And in the second case, let's keep the charge magnitudes constant and vary the distance between them. We find that theta is proportional to 1 by r square. So combining, we get theta is proportional to Q1 Q2 by r square. That proves the law practically. That is, F is proportional to Q1 Q2 by r square because F is proportional to theta. So till now we have seen how to calculate force between 2 point charges. Now what happens if there are multiple charges, multiple point charges in a space? That is usually the case. So here we shall find out what happens when there are multiple point charges present. We need to calculate electrostatic force on a particular charge due to all other point charges surrounding it. Let's say we have charge Q1 and we need to find out the net electrostatic force on Q1 due to all other charges, that is due to charge Q2, Q3, Q4 and so on. This can be done using a simple principle called as superposition principle. It's a beautiful yet simple principle. The principle states that the net electrostatic force on a specific point charge due to all other point charges in the space is given by the vector sum of all the individual forces due to individual charges. That means F1 net is equal to F12 plus F13 plus F14, so on. So this beautiful relation will help us to solve many problems in electrostatics, where you will be given problems. You have one charge and many charges surrounding it, and you need to find out the net electrostatic force on it due to all other charges. Thank you. Let's continue more in the next video.